How did Earth go from this to this? Two and a half billion years ago, the single most important event in our planet's history happened. And the trigger that caused it isn't what you would expect. If you found yourself dropped into early Earth, you would think that you were on an alien planet. Simply breathing in the air would be enough to kill you. The atmosphere was dense with methane and carbon dioxide. The sky had an orange haziness to it. And the oceans weren't blue. They were green and rich in dissolved iron. But this wasn't an alien planet. This was Earth. And this was how it was for the first 2 billion years of its existence. Until something changed. Something so impactful that it's been referred to as the single most important event in our entire planet's history. And it wasn't a meteor strike or a volcanic eruption. It was cyanobacteria. These tiny single-celled organisms had their eureka moment when they worked out how they could turn sunlight and water into energy. And in doing so, they inadvertently flooded the planet with a waste product that wiped out almost 80% of all life. That waste product was oxygen. And this event, called the Great Oxidation Event, is why we exist. So let's set the scene. Picture yourself on Earth roughly 2.5 billion years ago. It looks something like this. Earth at this point is already middle-aged by planetary standards, and life has existed for at least 1 billion years, but it's not life the way that we know it. The atmosphere is completely different. Oxygen, which comprises around 21% of the atmosphere today, is more or less absent. And instead, the atmosphere is what we refer to as reducing and is dominated by gases like carbon dioxide, methane, and hydrogen. Now, of these, I want to focus your attention on the methane. You might know it as one of the main ingredients in a fart, but it's also a very potent greenhouse gas and is around 30 times more effective at trapping heat than carbon dioxide is. During the Archean, there was likely hundreds of times more methane in the atmosphere than there is today. Now, the good news is that methane doesn't actually have any odor, so there's nothing to worry about with Earth's Dutch oven era. But it did heavily contribute to the greenhouse effect, keeping the Earth warm despite the fact that the sun at the time was only around 70 to 80% as intense as it is today. Life at the time was pretty much entirely comprised of anaerobic organisms, organisms that don't use oxygen and, in many cases, find it toxic. These organisms obtain their energy from a wide variety of sources. Some extract it directly from minerals. Others practice a form of photosynthesis that doesn't produce oxygen, called anoxygenic photosynthesis, where rather than water, they use compounds such as hydrogen sulfide or ferrous iron to provide electrons. The oceans of the time would also have been unrecognizable. I already mentioned that they would have been pale green in color as a result of all of the dissolved iron that was found in them. To put it into perspective, it's likely that the iron concentrations were hundreds to thousands of times higher than what we see in modern oceans. And this iron was going to play a critical role in what was to come. It's important to note, though, that oxygen was being produced even before this, but only in very small amounts and very specific cases. One such example is the splitting of water molecules in the upper atmosphere by UV radiation from the sun. But the oxygen never accumulated because as quickly as it could be produced, it reacted with methane, hydrogen, minerals like iron, and volcanic gases. And these formed enormous oxygen sinks that prevented oxygen from accumulating and kept atmospheric concentrations at effectively zero. So, the stage is set. Life was anaerobic. The atmosphere was reducing. The ocean is rich in dissolved iron. And then, it happened. Enter our heroes, or villains, depending on your perspective, cyanobacteria. See, around this time, cyanobacteria invented oxygenic photosynthesis. Unlike existing photosynthetic organisms of the time, who were using hydrogen sulfide or iron as their electron donors, cyanobacteria make use of water, the most abundant molecule on our planet. This relatively simple substitution had a huge impact, because when cyanobacteria use the energy from photons to split water, the only things they're interested in are the hydrogen and the electrons, so they release the oxygen as a waste product. Now remember, other photosynthetic organisms aren't using compounds that contain oxygen, so there's no way for them to release it. Think about it. The very air that we breathe today only exists because 2.5 billion years ago, cyanobacteria started treating oxygen as trash. Interestingly enough, the origin of oxygenic photosynthesis can be seen as a kind of evolutionary singularity, because as far as we can tell, it only ever happened once. Every organism on the planet that we know of that's capable of performing oxygenic photosynthesis seems to have acquired it as a result of cyanobacteria evolving it originally. But when did this happen? Well, it's a little difficult to say for sure, but most of our evidence points to the origin of oxygenic photosynthesis in cyanobacteria being dated to around 2.7 to 3 billion years ago. But hang on, if cyanobacteria evolved oxygenic photosynthesis so early, why did it take so long for the Great Oxidation Event to take place? Well, the likely answer is that initially, cyanobacteria probably only occupied a few different environments, like shallow waters, microbial mats, and maybe lakes. And because of this, they had restricted range and weren't producing too much oxygen, which was being consumed almost immediately by those vast chemical sinks that we discussed earlier, so that none of that oxygen could accumulate. There are traces of these whiffs of oxygen, transient, very localized increases in oxygen concentrations that weren't sufficient to cause a permanent change in the atmosphere. They can be seen in things like oxygen-sensitive elements like molybdenum, rhenium, or sulfur isotopes. But it's important to note that more recent research has challenged this, suggesting that later geological processes could be responsible for what we see in the rock record. So, where are we? Well, we're confident that cyanobacteria evolved the capacity for oxygenic photosynthesis well before the Great Oxidation Event truly started in earnest, and that for a long time, processes were preventing the oxygen that was being produced from accumulating in the atmosphere to significant levels. So for hundreds of millions of years, despite cyanobacteria's best efforts, the Earth remained anoxic. So what changed? Well, sometime around 2.45 to 2.4 billion years ago, Earth reached a tipping point, and oxygen began to accumulate. But this wasn't a single moment. It was a gradual transition that took place probably over the course of around 200 to 400 million years, during which oxygen levels in the atmosphere gradually rose to reach around 1 to 10% of modern levels. But if you're imagining that this was a steady transition to oxygenation, then that's not how oxygen levels rising happened at all. The latest research suggests that the rise in oxygen was neither smooth nor monotonic. It was chaotic and oscillatory. And it's likely that the Earth lurched towards oxygenation multiple times, briefly achieved it, and then slipped back into anoxic conditions until eventually the transition stuck. So what are the actual factors that triggered the Great Oxidation Event? Well, it's been suggested that there were several interconnected processes that together triggered it. First, as they became more successful, it seems likely that cyanobacteria were able to expand their range from those limited environments in which they originally evolved into the open ocean, which vastly increased their capacity to generate oxygen on a planetary scale. Secondly, certain geological processes may have contributed to reducing the size of the oxygen sinks. As Earth's mantle became gradually more oxidized, volcanic gases contained less reducing power within them. As less hydrogen and methane was being produced from volcanoes, that meant that less oxygen could be consumed by them. Third, hydrothermal vents may actually have slowed down the rate at which they were releasing iron, thus reducing the amount of dissolved iron in the ocean, contributing to the reduction in the size of the available oxygen sinks across the planet. Fourth, in 2021, a mathematical model suggested that at least partially the GOE was contributed to by ecological competition. See, initially, anoxygenic photosynthetic organisms dominated because their electron donors, such as ferrous iron, were highly abundant. As the abundance of ferrous iron decreased relative to the amount of phosphorus, cyanobacteria gained an advantage, allowing them to take over more of the photosynthetic niches on the planet, thus producing more oxygen. Regardless of the specific trigger or triggers that caused the GOE, once oxygen started to rise, positive feedback loops continued the process. A thin ozone layer formed in the Earth's lower atmosphere, which reduced the rate at which reactions that produced and destroyed methane were taking place. With less methane destruction, but also less production as oxygen reacted with it, the greenhouse effect was weakened. And that's when things got really dramatic. But before we get into what happened next, how do we know any of it happened at all? Well, the evidence is quite literally written in stone. Some of the most iconic evidence for the GOE comes in the form of these vast banded iron formations that we see right across the globe. These are visually stunning, enormous sedimentary deposits of iron-rich minerals and silicate. Banded iron formations, such as this one, are the result of ferrous iron coming into contact with oxygen in the Earth's oceans. As oxygen levels increased, it reacted with this ferrous iron and oxidized it to ferric iron, which then precipitated out as iron oxide. It's the same as the rust that you see on old metals, forming these bands of red and black minerals. The fact that these banded iron formations are relatively common before the GOE, but not afterwards, tells us that suddenly oxygen became available. Then there are these red beds. No, not that kind of bed. Terrestrial sedimentary rocks that get their rust color from iron oxides. These are only seen after the GOE because they require oxygen to oxidize the iron and form them. Prior to the GOE, ancient soils and river sediments show no sign of oxidation. One of the strongest pieces of evidence comes from sulfur isotopes. See, in an atmosphere with no oxygen, a process called mass-independent fractionation takes place, which leaves behind a very distinctive chemical signature. However, once oxygen levels started to rise and the ozone layer formed, it prevented the UV radiation that was necessary in order to drive these processes. We can see in the geological record that this mass-independent fractionation of sulfur isotopes disappears at some point. And by dating it, we can place the GOE squarely around 2.45 to 2.43 billion years ago. There are other evidences as well, such as the disappearance of detrital pyrite and uraninite. These minerals are unstable in the presence of oxygen, so before the GOE, they appear widespread as they're transported across the planet by rivers. After the GOE though, they disappear as a result of rising oxygen levels. And then we have the Lomogundi carbon isotope excursion, a large prolonged spike in the carbon-13 content of carbonates that started shortly after the GOE, sometime around 2.22 to 2.06 billion years ago. This signals a major reorganization of the global carbon cycle, linked to increased burial of organic carbon, which in turn likely resulted in increased release of oxygen. The Great Oxidation Event wasn't all sunshine and rainbows though. At the time, it was a major ecological disaster. For the anaerobic microbes that comprised the majority of life at the time, oxygen was toxic. Highly reactive oxygen species like hydrogen peroxide and superoxide attack organic molecules, damage DNA, and destroy cellular machinery. And these organisms lacked the protective measures required to defend against this. The rise in oxygen levels likely triggered Earth's first mass extinction event. Quantifying just how much life was lost is difficult because all life was microbial, and microbes don't really leave behind much in the way of fossil evidence. But estimates from the geological record indicate that the biosphere shrunk by around 80%. The survivors of this were pushed into marginal environments where oxygen couldn't penetrate, like deep sea sediments, or sulfur-rich hot springs, and eventually animal guts. Their descendants are still there today, living reminders of Earth's anoxic past. But life constantly reminds us that there's opportunity in adversity. And for the organisms that could tolerate and even use oxygen, this represented a huge chance. Aerobic respiration is a much more efficient metabolism than the anaerobic metabolisms that were around at the time. To give you an idea, glycolysis, which is anaerobic, produces only 2 ATP, the energy currency of cells. If we add aerobic respiration into the mix, we get 36. That's an 18-fold increase in energy yield. The increased energy efficiency was a boon to life. More energy meant bigger cells, more complex biochemistry, eventually multicellularity, and around 1.5 billion years later, animals. The GOE also gave us our ozone layer. As oxygen levels increased, O2 molecules in the upper atmosphere reacted with UV to be split into individual oxygen atoms. These oxygen atoms then mixed with O2 to become ozone, O3. That ozone forms a shield, a protective barrier preventing UV radiation from reaching Earth's surface and making the entire planet much more hospitable to life. But oxygen's rise had another devastating outcome and may have plunged Earth into its first global ice age. Remember the methane greenhouse that we were talking about earlier, and how methane is highly reactive with oxygen? Well, as oxygen levels rose, it reacted with the methane in the atmosphere and split it into carbon dioxide and water. As I mentioned earlier, carbon dioxide is a less efficient greenhouse gas than methane, and so the result was a weakened greenhouse effect. Temperatures plummeted, and ice spread from the poles towards the equator. And as it reached around 30 degrees latitude, a positive feedback loop referred to as the ice albedo effect took over to ensure that it would continue. As more ice accumulated, it reflected sunlight back into the space, reducing the amount at which it could heat the Earth. This resulted in more ice accumulating, more sunlight being reflected, and eventually, the Earth being covered with ice. This is called the snowball Earth hypothesis, and the Paleoproterozoic version of it may have been entirely caused by the GOE. The geological evidence that this happened comes in the form of diamictites, mixtures of rock and mud that form as a result of glaciers. In South Africa, in the Makanyane Formation, we find such deposits alongside volcanic rocks that could be traced to tropical latitudes. And if glaciers manage to reach tropical latitudes, then that must mean a global ice age. But there's a twist, because the exact same geological evidence suggests that massive volcanic eruptions that formed the Onchuk Large Igneous Province took place just after the glaciations. These eruptions pumped CO2 into the atmosphere, compensating for the loss of methane, restoring the greenhouse effect, and triggering a global thaw. The GOE, the snowball Earth, and the volcanic rescue are all connected, all part of the same overarching event. The Great Oxidation Event is one of, if not the most, impactful events in our planet's history. It transformed our atmosphere from anoxic to oxic. It created the ozone layer. It also triggered a global ice age and killed 80% of all life. But it led to the evolution of aerobic life and eventually us. But the GOE isn't solely responsible for making our atmosphere what it is today. And levels of oxygen after the GOE weren't at the same amount that they are right now. It's likely that oxygen afterwards was only around 1 to 10% compared to 21% that we see today. The next 1.5 billion years of our Earth's history are referred to as the boring billion. During this time, oxygen levels stayed fairly low. The deepest parts of the ocean were still anoxic, and life was still microbial. It wasn't until a second event, the Neoproterozoic Oxygenation Event, around 800 million years ago, that oxygen levels reached amounts similar to what we see in the modern day, and complex life exploded onto the scene. The GOE was a necessary first step, but it didn't unlock everything. Evolution takes time. Today, we still have cyanobacteria to thank for around 50% of the oxygen that we breathe. We can find them across the planet, in the oceans, in lakes, and in damp patches of soil. The descendants of these pioneering microorganisms are still hard at work, making the air that we breathe. Next time you take a deep breath, remember that oxygen has been on a journey. It was once poisonous to most life. It caused a mass extinction, froze the entire planet. And now, it powers your every thought, your every heartbeat, your every movement. The Great Oxidation Event is an amazing example of how life doesn't just simply adapt to its environment. It also transforms it in ways that are sometimes catastrophic. Those tiny cyanobacteria that evolved 2.4 billion years ago had no idea that what they were doing would create the planet that we have today. They were just trying to survive, but they gave us everything. Thanks for watching. If you found this journey through deep time interesting, then hit the like button and hit the subscribe button if you want to stay in tune for more content about Earth's history. Until then, breathe deeply and remember to thank your local cyanobacteria.